So hi everyone, happy to be here, even though not physically. As Avi said, my name is Galia. I'm a PhD student at Weizmann. My advisor is Guy, who is also in this picture and on this call. And today I want to tell you about this kind of recent line of work. The title is Multi-Group Learning via Outcome Indistinguishability. This is joint work with Cynthia Dwork, Michael Kim, Omer Reingold, and Guy. And Avi told me it's a rather informal setting, so please feel free to kind of interrupt me at any point, and hopefully I would have some answers for you. Okay, good. Let me do my cursor. Okay, good. So the backdrop for this talk is the fact that, as you must have heard a million times by now, as machine learning and algorithmic decision making in general is widely deployed, there are a lot of really cool advances, but also we're increasingly hearing about these kind of adverse side effects. And these are kind of three particular audits that of algorithms that are currently, or at least have been deployed, which I'm kind of especially, I found them especially interesting. The first is an example in the healthcare system in the US, where there's an algorithm that's driving healthcare decisions about who gets additional care, and was found to be like really racially biased. It's a very interesting example. There's been a lot of work on Facebook's ad delivery and how it's skewed across lines of race and gender. And there's also a very famous example that demonstrates that kind of so-called state-of-the-art face recognition tools actually have really low accuracy when you evaluate them on subgroups in the data, specifically darker skinned females. This is an example that I'm gonna kind of revisit in a bit. Sorry. Okay, so this has led to this kind of subfield of algorithmic fairness, or looking at it specifically from a computer science perspective. At this point, I think we're like almost 10 years into this research agenda. It's pretty clear that there's not going to be like a one-fits-all solution. One issue is that fairness kind of as a concept is very context dependent, and it's something that's often hard to like build into these formulations. And also the kind of the machine learning setup that we're talking about is, in some sense, it's a pipeline. It's composed of formulating the problem, gathering the data, and then the learning procedure itself. And issues that arise at different stages of this pipeline often call for different types of solutions, in a sense. So I think the place where things are at is kind of very naturally calls for more theoretical work, right? Like we really want to understand, want to articulate definitions, and want to understand what's possible and how can we achieve it. So the perspective that I'm going to present here is very theoretical, and it's also focused specifically on harms that are potentially introduced in the learning procedure itself. So a good example to keep in mind is something like this gender shades audit that I've discussed, where kind of the task itself, the problem formulation is okay. So maybe the case here is that given an image of a face, we want to say whether the person is smiling or not. And the data is also reasonably okay. There is like examples of specific subgroups, but we are concerned about biases in the learning procedure. For example, the eventual accuracy being very low on some subgroups. Okay, so roughly there will be two parts to today's talk. The first, I'll discuss this notion of outcome indistinguishability, or OI, which is a new desideratum that we put forward for prediction algorithms, which, as you'll see, is kind of inspired by concepts from complexity theory and cryptography. And in the second part of the talk, I'll discuss how we can use this framework to kind of learn predictors that have stronger semantics or stronger guarantees towards subgroups in the data. Okay. Okay, at one point I will figure out what's the next and what's the previous. Okay, so right towards coming up with this desideratum, like there is a subtle point here, right? On one hand, the entire premise of prediction is to actually make distinctions between individuals based on their observed attributes. But on the other hand, I've just argued that some of these distinctions that algorithms end up making or not making may actually end up being harmful towards groups of individuals. So the perspective that I'm going to kind of present today is in some sense replacing this question of what do we want from predictors with trying to kind of build up towards articulating specific harms and then seeing how we can prevent them. Okay, so just to have like the setup that I'm going to discuss for the rest of the talk in mind. So think of some domain X. So maybe this is a person's entire medical history and a binary outcome space Y. So maybe this is whether they had, I don't know, a heart attack in a 10-year follow-up. And there is some joint distribution, D star on X and Y, which is unknown. And I'm interested in learning or reasoning about risk predictors, which formally are mappings from this domain X to the interval 0, 1. Okay, so in this example, everyone kind of at the top is receiving a prediction of 0.9, and everyone here is receiving a prediction of 0.2. And we'll be thinking of setups where these predictions end up informing some binary decisions. So for example, everyone whose predicted risk is larger than 0.6 receives some kind of a resource. So maybe it's extra medical attention from their doctor or something like this. Okay, so here everyone receives, all the green people receive a prediction of 1 and all the yellow a prediction of 0 because they're below the threshold. And we're going to have some subgroup in mind, S. So this is a subgroup that's defined in terms of the feature space. And specifically here, it gives us a partition into people inside S and people outside S. And the question I want to kind of start with is, given this demographic group of interest, so maybe this is women, which predictors are we concerned about in the context of this setup? Okay, so let's look at like an immediate kind of simple example. So something that I can do if I want to harm the members of S in this context is I can just assign everyone in S a low predicted risk in a way that's completely irrespective of their actual outcomes. Okay, so what we see here is for people outside S, this predictor is actually managing to make meaningful distinctions. It identifies that this part of the space is high risk individuals. It gives them a prediction of 0.9. This part are lower risk individuals. It gives them a prediction of 0.1. But for everyone in S, it just kind of gives up and just gives everyone a prediction of 0. And consequently, they get also a binary decision of 0. So they don't get any medical attention or whatever. Okay, so here there's kind of an obvious sense in which this predictor is bad, right? If you look at S, you see that the predictions are kind of blatantly inconsistent with the empirical data that we have at hand, in the sense that the expected outcome Y conditioned on being in S is a half, but the expected predictions are 0. So there's like this obvious mismatch here. So this is the first example. We're going to revisit it. And the second example is just a minor modification on this example, where now for everyone in S, I'm not just giving a prediction of 0, I'm giving them their expected outcome as a group. Okay, so here maybe the expected outcome is a half, And I'm just giving everyone in S a prediction of a half. And note that since a half is smaller than this threshold of 0.6, it ends up being the same in terms of this binary decision. Still, no one in S is getting this resource. Okay, so here the issue is, as you can already see, it's a bit more subtle, right? Like this notion of consistency with the data that I discussed before. Here it's okay, but there's a subgroup of S. So, right, like maybe I can, draw a subgroup around these people. And for them, it's still this blatant inconsistency, right? Like they have a high conditional outcome, but I'm still giving everyone a prediction of a half. So in this sense, this example is a bit more complex than the first one. So I'll revisit these examples, but let's set up some additional notation. So I'm going to denote by P star the Bayes optimal predictor. Okay, so this is the expectation of Y conditioned on X. And as far as this objective that I've discussed before for preventing harms in the learning procedure, P star is optimal, right? Like if I had infinite data, I could compute it exactly. So using P star, we can derive a different perspective on this joint distribution D star. I can view it as the joint distribution on X and Y that's obtained by first drawing an individual according to the marginal distribution on X, and then drawing an outcome by tossing a coin with bias P star of X. Okay, so this is a completely equivalent view. So at this point, I haven't done anything interesting, but I want to say that this view now gives me kind of suggests that for every other predictor that I'm coming up with and is not necessarily P star, this predictor also similarly defines a joint distribution on X and Y, right? I can draw an individual X from the marginal distribution, but this time I can draw an outcome that is not the real outcome, and I'm going to call a modeled outcome by tossing a coin with bias P of X. Okay, so this distribution, I'll denote it d tilde of P, and it's important that it's parameterized by the predictor P. And it's actually going to be kind of an important component in this framework. So we'll revisit it.
So Gal, this modeled outcome is independent of X.
Sorry?
The modeled outcome is independent of X, no?
So the modeled outcome is you first draw an X, and then you take a coin toss with bias P of X. So
it depends on the predictor. Okay, yeah.
Yeah, if the predictor is making distinctions, then the modeled outcomes also depend on X. Okay. So let's revisit these example with this D star and D tilde in mind. So this is the first example where, as you remember, everyone in S just receives a prediction of 0. So D star looks right like this is the same. I'm just copy pasting. But for D tilde of P, what I'm doing here is I'm generating outcomes, one per X, by drawing a Bernoulli with bias according to P. So in particular, everyone in S is receiving a modeled outcome of 0 because I'm just drawing from a coin that has bias 0. Okay, and with this D star and D tilde, there's like a more obvious sense in which P is a bad predictor, because the outcomes on the left, the real outcomes, clearly look different from these modeled outcomes on the right, right? Like in a silly sense, here I'm not seeing any ones, and here I am seeing some ones. Okay, so let's formalize exactly this notion of looking different. We're going to use a distinguisher algorithm. So formally, a distinguisher algorithm receives a sample, so an X and a binary outcome Y. And it can do two things. It can accept output 1, or it can reject. And the discussion that we've just had suggests that kind of a good predictor is such that this distinguisher algorithm behaves similarly, irrespective of whether the sample it receives was drawn from D star or from d tilde, this modeled outcome distribution. So in particular, the probability that A accepts on inputs from D star should be similar to the probability that A accepts on inputs from D tilde.
Got it. But this would not be the same. You will not have this in the previous example if for all the people out of X you gave the treatment, and right, and then maybe this over the whole distribution it will look fine, but not on specific subset.
Yeah, exactly. So this suggests that I need to kind of choose this distinguisher algorithm carefully. If all the distinguisher does is look outside of S, then things might look completely fine. Right, so let's actually do this example kind of as you suggested to the end. So here I'm defining a specific distinguisher that I'm denoting A sub S. And this is like a simple expectation tester for this subgroup S. So basically what it does is it first looks if the individual is coming from S. If it is, it's outputting Y. Okay, and I want to claim that the predictor that gives everyone in S0 fails the test that I've just described with respect to this distinguisher A sub S. Okay, and this is fairly straightforward. I can just derive the probability that A accepts on inputs from D star. This is exactly the probability that Y is 1 and X is in S, which is the mass of S times the conditional expectation of Y in S, which in this case is a half for the real distribution. But for the model distribution, I follow the same calculation, but now I have mu of S times 0 because the conditional expectations of outcomes in S for the model, for the predictor is actually 0. So, you know, if for small enough epsilon, as we'll soon see, this mu of S times a half is different from 0. Okay, but on the other hand, just to emphasize, so if I move back to the second example, where now everyone receives a prediction of a half, this time this predictor does pass the test with respect to A sub S. Okay, this is kind of what Avi was also hinting towards. Here, the expectation, here the probability of acceptance is mu sub S times a half in both cases. So if we think about it, when should this predictor that's giving everyone in S a half, when should it bother us? So I want to say that it bothers us if there was really a way that we could a priori identify in the data a subgroup S that of S, sorry, that should have received a higher prediction, higher predicted risk. For example, if I could identify from the data that these are, say, women that also have asthma, and for them, we can see that this predictor would fail with respect to A sub S prime, this new group that I formed. Okay, so this somehow speaks to the fact that this desideratum, we should think of it with respect to kind of an expressive or sufficiently rich class of distinguishers that would allow us to capture these types of behaviors. Okay.
What about what happens in scenarios, I assume similar to what you have here, where you do have some access to knowing what the real answer is or what the real data should be, and this means that you might not be able to a priori identify a group for which you would be wrong, but even if you are right in the terms of the proportion of people in this group that add something, but you just answer randomly with this probability for any person, you would obviously be much more often wrong about classifying certain people within this class without being wrong on an a priori class of people.
I'm not sure I exactly followed your.
So let's try to state it better. I'm saying that let's say I have males and females, and I want to check who has asthma according to a picture of their lungs or something. And for the males, I would just be able to identify it very well. Like from a lung picture, I could very well tell who has asthma and who doesn't, and they classify according to this. But for the female group, I wouldn't do anything except of just taking the proportion of females that should have asthma and guess for any particular person with this probability. So what predictor would you use in this type of case to identify this?
What distinguisher would I want to rule out this type of behavior?
Yes, what distinguisher?
Okay. Yeah, so you're saying kind of similar to this example, but now I'm drawing from P of, say, a half.
I'm saying that there is something that maybe you can't identify in advance because this is your entire purpose, right? Finding who has asthma.
Okay, I think I have like exactly a slide that's kind of relates to this question. So let's revisit it in 10 minutes if you haven't gotten an answer.
Okay, thanks.
Okay. Any more questions? Okay, so maybe I'll use this to kind of formally define this notion of outcome indistinguishability, or OI. So formally, I'm going to say that a predictor P satisfies outcome indistinguishability with respect to a distinguisher class A and kind of an accuracy parameter epsilon, if no distinguisher in this class can tell D star from D tilde with success probability that's greater than epsilon. Okay, so this is exactly what I've described. And just to note, the strength of this guarantee naturally depends on this class of distinguishers, but even with an unbounded class, this still might not be like a single person's true individual risk, right? I'm always operating in this feature space X. So in some sense, this gives us a computational perspective on this question of individual probabilities, which has been kind of long studied in different communities. And one perspective that I'll discuss kind of in the next few slides is this question of learnability, or how many samples do I need to see from the real distribution D star before I can learn a predictor that's outcome indistinguishable. So I'm going to say that a family of distinguishers A is learnable with sample complexity M if there is a learning algorithm that for every accuracy parameter epsilon and success probability delta, and for every distribution D star, if the algorithm receives more than M epsilon delta samples drawn from D stars, then the thing it returns is with high probability satisfying A epsilon OI. Okay, so this
it doesn't have to be a member of A though.
Yeah, it doesn't have to be a member of A. In fact, right, like A, as I've defined it, is the range is like the set 0, 1. So it's even a slightly different creature. But yeah, it's similar to like learning, where we want to compete with some family, but we don't necessarily care about outputting something from this family. Okay, so just to kind of discuss some perspectives before I move on to what I mentioned might answer all's question. So first is this scientific method perspective. So there's a nice talk where Neumann, I forgot, sorry, I'm blanking on his name, but but he discusses kind of how to look for a new law of physics. So he said basically there are 3 stages. First, you guess it, then you compute the observable consequences of what would you expect to see in the world had that guess been correct. And if those consequences disagree with what you actually see in the world, then your proposed law is incorrect. And this, first of all, it suggests that kind of scientific theory will only be in the status of being temporarily right? Like until we have, I don't know, better telescopes and we can see in which ways the observable consequences differ from nature. But this is very similar to this perspective that I'm presenting here, in the sense that maybe a predictor kind of looks to be outcome indistinguishable as far as my current data representation or my current distinguisher class, but maybe in the future I would have better data representations or more kind of computational resources, and I actually would be able to find ways in which this predictor differs from the outcomes that are generated in nature. This is one perspective, and another natural perspective or connection is pseudo-randomness, right? So that is like the study of simple and deterministic objects that can look like high entropy distributions to computationally bounded observers. And here it's similar in the sense that P star, this Bayes optimal predictor, for all we know, it could be arbitrarily complex, but this kind of framework of OI says that, okay, we can generate models that are potentially much, much simpler in terms of their complexity from P star, but we can somehow proceed as if we are actually using P star, as long as what we're doing afterwards comes from, in some sense, also a bounded class of computations. Okay, good. So I want to touch on kind of an important piece in this definition, which is the degree of access that the distinguishers in question have to the predictor P. And as I've currently defined it, they don't really have direct access to the predictions, right? All they're seeing is these binary outcomes that in this case are drawn from the predictor, but they're not actually seeing the prediction itself. So in this sense, I'm calling this variant of OI with respect to such distinguishers, no access OI, in the sense that it doesn't have direct access to the predictor in question. And you might ask, okay, like why is this an issue? So I think this is where it maybe relates to All's question. So consider a predictor that just a P star, a Bayes optimal predictor that is just a half for everyone. Okay, so there's not like any signal in this case, but the predictor that I'm worried about is kind of chooses some random subgroup of the feature space that, say, has mass a half. And for that subgroups, it assigns a prediction of 1, and for the others, it assigns a prediction of 0. So this is, it's not clear that we like this predictor, right? Like it's making distinctions that are not actually borne out in the data. But if I would want to rule out this predictor with no access OI, what I would want to do is I would want to have an expectation tester of the type that I've described before that tests the expectation of this subgroup B, right? Because then I would see that the expectation is 1, even though in the real outcomes it's a half. But the issue here is that this group B, it's not really defined a priori from the data, right? In some sense, it's only kind of defined a posteriori once I also have the predictor in question. So ruling out this type of behavior without actually having direct access to the predictor is going to be very challenging. I have to kind of include expectation testers with respect to all potential subgroups in the data, and this would be a collection that's exponentially large. So this is not what we want, and really there's an easy fix. By giving the distinguisher direct access to P, we can define something that's a bit more complex than these expectation testers that I've defined. I'll call this a calibration tester, where basically by getting the value of P directly, I can specifically kind of restrict my attention to level sets of the predictor. So in this case, I would just be able to look at the group for, that's defined by everyone receiving a value of 1, which is exactly B, without having to include it ahead of time.
How do you think of P? So you think of P as something that is not binary?
Yeah, it's a fraction.
Yeah, but I mean, what if it is binary? What if it is like a classifier that just assigns binary values to each input?
But did you say B or P?
P.
So in general, P it gives something in the interval 0, 1. Here I just have an example where it actually gives binary values.
What I'm saying is that the same example that you just gave could also hold in the case that P star, what you want to learn, might be fractional, but P could be binary because it is binary in your example, actually. So even with access to P, it's not clear what you would do about this.
Right, but that's like an orthogonal question.
I guess I'm asking.
Why is it not clear? With
I'm
access
asking
to
how does access to P change anything in this particular example where P is just what you are seeing by a sample out of it, right? If it's binary. I mean, I guess I'm missing something. If I understood correctly, you are saying that there is a difference between sampling X and then Y that is drawn according to P, then to see actual, like to draw an X and see P of this X, or are you saying that you see P in some stronger manner than that?
So the only, here is the formal definition. The only difference between this addition level, I'm still sampling an X from the marginal distribution, sampling an outcome Y from either P of X or P star of X, depending on which side I'm on. But in both cases, I'm also giving the distinguisher access to P of X for this sampled individual.
Okay, so if P is binary, then P of X and Y are the same, right? Yeah. So this particular problem that you sketched here, it doesn't matter if you get access to P or not, right? Because Y and P of X are the same.
They're the same on the right-hand side, but not on the left-hand side.
Yeah.
So if you look at the examples,
right, the real thing, P star, how would you be given access to?
No, but I'm not given access to P star. I'm giving P of X also on the left-hand side when I'm taking samples from D star.
Okay,
but this is different from, yeah, as Guy's saying, this is the case where this is different, because now I can test something that's a function of the real data, but I can also test it on subgroups that are defined by P, which I couldn't do beforehand.
So putting it very simply, the distinguisher that looks at the x's for which P of X is equal to 1, on the left-hand side, half of them will be zeros, will have Y equal 0, and half of them will have Y equal 1. And on the right-hand side, they will all have Y equal 1. So these are very distinguishable.
Okay, I see. So this is, I mean, but you would get the same thing just by looking at, okay, so the difference is that you are not looking at Y of the right-hand side, but you're looking at the real Y, in a sense. It's not the same Y.
Mm-hmm. Yeah.
So I think that's actually, maybe I'll say something. We have this predictor P. Someone is claiming that this is how the world works. And kind of the indistinguishability requirement says is that it should be, given this P, we know what it is. Things should look the same, whether the actual Ys are drawn according to this P in sort of the modeled world, or in the real world where the Ys are drawn by P star. We shouldn't be able to distinguish the two, but the P is the same P. That's the model we've been given, and we're trying to distinguish or refute whether it's incorrect.
Okay, cool. Thanks, Guy. I Okay, so this is kind of the second level of the hierarchy that I'm calling sample access OI. And with this kind of additional access that I gave the distinguishers to P, you could also imagine a third level of this hierarchy where now they have kind of oracle access to P. So in particular, they can query for the predictions of individuals that are not necessarily the sampled individuals. This is the difference from the previous level. Okay, so this is a kind of a hierarchy of definitions of OI. And first of all, in terms of kind of relating it to also to previous works and to these types of expectation testers and calibration testers that I've described. So you can actually show that no access OI is equivalent to this concept of testing expectations of subgroups. And similarly, sample access OI is equivalent to testing for calibration across subgroups. Okay, and these are notions that have been previously studied in this earlier work on multi-calibration. Also interesting is that there isn't an analog for this more complex idea of oracle access OI. And in terms of the sample complexity, so we obtain upper bounds on the sample complexity via kind of a specific learning algorithm that directly constructs OI predictors based on whatever level you wish. And these upper bounds are kind of for the two levels, no access OI and sample access OI. They are nice in the sense that the dependence on the accuracy parameter is polynomial, and the dependence on the number of distinguishers is logarithmic. So this constitutes kind of a regular learnability. Whereas for the more complicated notion of oracle access OI, they actually give rise to an exponential dependence on the accuracy parameter. And in the paper, we actually showed that under reasonable assumptions in fine-grained complexity, this can't be improved. So it's not just kind of a bug with our algorithm, but there's an actual barrier there. So that's one thing. And I also want to mention that all of these notions, I've defined them for single sample distinguishers, but they can be extended for multi-sample distinguishers. And I'll actually make use of it in this second part of the talk. Okay, so maybe I'll stop for see if there's any additional questions.
Yes, I'm sorry to go back to this, but considering Guy's answer, I want to ask the following thing. What about the thing between no access OI and sample access OI that just uses the fact that you have this coupling? So let's say that I don't give you access to P of X, but when I draw X, I give you both Y from the real distribution and Y from your tester.
You're asking whether it buys me something?
So I'm saying that what Guy sketched as why it helps is, at least in the binary example, is just that, right? The fact that I see the same X and the real value and the wrong value. I don't really need P of X in that example. So my question is, do you really need P of X in the general thing, or is it suffices to just see both of the Y's at the same time?
Yeah, Guy, do you want to say something?
Do you want to say something? So I think mathematically what you're saying, I guess, compiles, right? Like it's something in between. You get, instead of getting where we had P of X, you get a sample from P of X. So that's more than getting nothing, but it's less than getting P of X. So mathematically, it sort of makes sense as an intermediate layer. Is that what you meant, Ol?
Yes, just because it sounds, it sounds reasonable in a sense, right? And also,
I wonder if the two, I wonder if it's actually equivalent to the sample access, like, but I don't know offhand what the answer is. I also don't have a clear motivation for why it's interesting, for someone who's trying to refute a certain model to give them the predictions of the model makes sense. Why you might give
because
them
this is what you
something that
see.
depends on the model, but isn't the model, I'm not sure, but mathematically it makes sense.
Maybe we'll delay to the end of the
Yeah,
talk.
sure. Thanks.
Okay, cool. Okay, so I'll jump into this second part. It's shorter, so I divided it into two parts, but they're not of equal size. Okay, and actually before I start, I want to mention kind of as an interlude that these ideas, right, as I described them, seem very kind of theoretical, but they actually have found their way into more practical applications, and I'll use maybe like a minute to mention one of them. So this is kind of joint work with people at Clalit, which is the largest healthcare provider in Israel, and the task that they're solving kind of on a daily basis is actually exactly what I've described before, right? Like they train these risk prediction models to identify people at high risk for various disease, and then they use these to drive decisions about who gets additional medical attention, and obviously fairness is a concern for them. So we've kind of considered this basic fundamental task of, say, predicting risk of cardiovascular disease. And here there's like this standard baseline model, which the clinical guidelines suggest that you use. This is a statistical model that's based on a specific list of predictors. And together with them, we've defined subgroups in the data. So basically taking a bunch of protected variables, looking at their intersections, and keeping all the subgroups that are sufficiently represented in the test data. So this gives rise to like 360 subgroups. Maybe one of them is like white females 50 to 59, low SES, and a history of immigration. So quite expressive. And when you look at the model, you can see that globally it's very well calibrated. But when you start to look at what happens on specific subgroups, it's very far from calibrated on these subgroups. So in this language of OI, this baseline predictor that's actually used on a daily basis does not satisfy outcome indistinguishability with respect to this class of calibration testers on these demographic subgroups that I've just defined. And when you run the algorithm that I've kind of was referring to as post-processing on this initial predictor, you can actually maintain accuracy and really improve this notion of subgroup calibration. Okay, so this is just to say that like these procedures, algorithmically, they're actually kind of lightweight, they're fairly interpretable, and they can be used to actually remedy these issues in practice. Okay, but now I'll get to the actual second part of the talk. So just to recap, we've defined this notion of OI, outcome indistinguishability. I've kind of hinted towards the fact that this captures something like this calibration across subgroups, that in some context, in some tasks, this seems very relevant. For example, this medical example that I gave, but it's also not clear why we would generally want it, right? So if I come back to this example of gender shades with disparities in accuracy, it's not really clear why calibration is even relevant here, right? Like there is the connection to OI that I've discussed, but it's not necessarily what we want. So I would say that what we really want here is some notion of good behavior, where this is task specific, but we want the predictor to display this good behavior simultaneously across subgroups of interest. Okay, so this is like a very high level idea of what do I mean by this notion of multi-group learning. And there's a question of how do you define this concept of good behavior. What I want to propose here is to interpret it in this agnostic pack sense. So if you haven't encountered it or you don't remember, basically the idea is very simple. We have some loss function that defines what does it mean to do well for the task that I'm currently considering. So maybe here this could be like 0-1 accuracy, whether I've correctly identified the person is smiling, yes or no. And what does it mean for a predictor to do well? It means that the loss that it obtains is competitive with some fixed class of predictors H. So it's no worse than the best predictor in this class. Okay, and this is,
you are willing to lose something.
yeah, I'm also going to be willing to lose, but as like a information theoretic concept, this is what I mean. Okay, so if this is what we mean by good behavior, I argue that this kind of naturally gives rise to this notion of multi-group agnostic pack, or multi-pack for short, where I have a rich collection of subgroups. So think of it as the subgroups in the example that I just gave. So maybe, you know, intersections of protected attributes. And what I want to ensure that simultaneously for every group in this collection, my predictor is such that the loss that this particular group experiences, so here D sub G is the distribution restricted to this subgroup, the loss that this predictor has on this subgroup is competitive with the best thing that this group could have obtained inside this class H. Okay, so basically taking this requirement and just putting this quantifier over the subgroups simultaneously. And this has been studied in the context of online learning in this recent work by Blum and Discrete. Okay, so if there aren't questions, I'll storm ahead. What I want to use kind of the rest of my time to show is that basically we can reduce this objective to OI, or basically if you've never heard of OI and you don't care about indistinguishability and you just want to do kind of learning with stronger semantics or stronger guarantees, then technically you can use the tools that I've just described to obtain this. Okay, so before I'll actually kind of sketch the idea for the reduction, which is fairly straightforward, I just want to mention like an asterisk about this this claim. So this notion of multipack that I've defined, if you think about it, it doesn't make sense for completely arbitrary loss functions because of the fact that the groups are intersecting, right? Like if I could define any loss function that I want, I could say that there is a subgroup A that only has a loss of 0 if it receives a prediction of 0, and another subgroup B that only has a loss of 0 if it receives a prediction of 1. And then if A and B intersect, then I'm never going to obtain this multi-pack guarantee because kind of I have to do something with the people in the middle. And if I choose to give them 0, one group is going to be unhappy. If I choose to give them 1, the other group is unhappy. Okay, so I'm going to show this reduction in the paper. We show this reduction for not for arbitrary loss functions, but in some sense for loss functions that are reasonable to use with this objective, in the sense that there is some solution. If you were not constrained at all, you could find a predictor that satisfies this requirement. Okay, but for now, just think of something very simple, which is that the loss is proper. Okay, so this is basically saying that this P star, or the conditional expectation, minimizes this loss. Okay, so you can think of squared loss, logistic loss, or also calibration loss. All of these are proper loss functions. Okay, so what do I want to do? Basically, I want to construct a distinguisher A sub Q, such that if P satisfies OI with respect to A sub Q, then I have this inequality, right? The loss of P is not much greater than the loss of Q.
So just a single distinguisher, not a family.
Yeah, so this is going to be a single distinguisher that gives me this thing on the right, and then I can just take a family of distinguishers A sub Q, one for every Q in H.
Okay.
So this is like a building block to show that. So I want to say that the argument is simple. It's a bit like the notation is a bit intense, but you don't even have to stare at it. I'll walk you through the 3 steps. Basically, I'm claiming that I can use this multi-sample distinguisher, A sub Q, which I'm formally defining here. So let's kind of give a sketch of why this distinguisher satisfies what I want. So first of all, one thing that's fairly obvious to note is that if this distinguisher accepts on samples from D star, then I'm done. Okay, and the way to see this is that when the distinguisher receives samples from D star, if it always accepts, it means this inequality kind of holds. And this inequality, basically the loss here would just be the loss of P, and the loss here would just be the loss of Q. Okay, so it's like a direct analog of what I have here. Okay, so if I can show that this distinguisher accepts on D star, I'm done. Okay, the second observation is that using OI, I'm guaranteed that the acceptance probability on D star and D tilde is similar. So it's enough to show that A sub Q accepts when it receives samples from D tilde. Okay, but here this will just kind of follow by construction, because using the fact that the loss is proper, I can show that A sub Q will kind of accept with high probability on samples from D tilde. Okay, this will just be kind of true by construction, because the loss here is just the loss of a predictor that's outputting the conditional expectation of the outcomes. And by the fact that the loss is proper, this is exactly the optimal thing to do. Okay, so this is hopefully it at least convinced you that there is a simple argument, even if you haven't followed all the details. Okay, so just to finish this claim.
So maybe, Gal, actually, maybe if you go back, maybe it's worth saying. So it's not, the details of the reduction are not so important, but I think what Gal is saying is that somehow there's if what your predictor is doing is, if we have a predictor and its loss is worse than the loss of some fixed thing Q that we know, then we can distinguish the predictions, we can distinguish whether samples are being drawn according to this predictor P or according to some other P star. Okay, where Q has better loss. Okay, so kind of if the loss is worse than some fixed predictor Q, there's a distinguisher that captures that, or catches that.
Mm-hmm. Yeah, thanks. Okay, so just to conclude the argument, so to show the reduction for the regular agnostic pack, I want to take a distinguisher family that has one of these A sub Q for every predictor in this class H. This would give me the agnostic pack guarantee. And now the translating it to this multi-group agnostic pack is straightforward. I just have to take a slightly larger family of distinguishers. Now I would have one distinguisher for every Q in H and G in G in this collection of subgroups, where the definition of this distinguisher is exactly the same as A sub Q, but it has this additional kind of pre-processing step where it filters the samples that it receives and only keeps the samples that are in G. Okay, so basically the same construction, and this gives me this notion of multi-pack.
What if some of these subgroups are very small?
Yeah, so this is going to translate into a larger distinguisher family, and I'm going to have to pay for it in the sample complexity of obtaining actually this predictor. But there is like a logarithmic dependence, so I could take potentially a family that's quite large. And the epsilon, sorry, the accuracy parameter.
Right? I mean, it should depend on the structure of G somehow, right? It could be that some of these classes, like their intersection doesn't exist in the distribution or almost doesn't exist in the distribution.
No, if it's consistent, you just want to make sure you pick enough elements from this subset. So
yeah, everything. Right. So everything I've said before was kind of for, for the empirical loss. I still need the step where I relate the empirical loss to the loss on the distribution. And that would mean I need to take the number of samples that this multi-sample distinguisher receives. That should be large enough to make sure that this thing is representative, even for the smaller subgroups. So I end up paying for it, but there's also like a linear dependence on K here.
What is K?
K is the number of samples that this multi-sample distinguisher receives. So this is a bit different from what I had in the beginning of the talk, where each distinguisher just received a single sample and had to say accept or reject. Now I'm actually giving it access to more than one sample at each decision.
I see.
Although I think, as Avi was saying to your question, if the subgroups are really tiny, tiny in absolute size doesn't matter. The question is, what's their mass in the distribution?
Yeah, I'm talking about tiny in terms of mass. I mean,
so you need to draw enough samples. You need basically the epsilon in the epsilon indistinguishability is absolute. So if you want a meaningful guarantee for tiny groups, you need a tiny epsilon. And that blows, as you would expect, you need more samples because you need to see people from these groups in order to get your guarantee.
Okay, so maybe I didn't get the definitions. I thought you restricted the loss to focus in a group and then the epsilon wasn't absolute, but maybe I didn't get this correctly.
Now, what she says is you get a big sample and you filter it through any particular G. So you throw away anything not in G. And you do it for every particular G. So you have to have enough samples to see enough samples from any G.
Okay, but what is this loss sub D of G? Is this, I mean, do you condition on being in G and then?
Yeah, I exactly the same. I restrict my distribution only to samples from G, and then I evaluate the error on that subgroup.
Okay, but then epsilon is not.
Epsilon is absolute for the outcome indistinguishability, not for the for this agnostic pack thingy.
So you the sample complexity would have to somehow depend on the mass,
the size of the smallest group. Yeah.
So, but you didn't tell us at all what situations you have an OI for. You have a reduction.
So we have. Yeah, so we have a general algorithm for constructing OI predictors. That's why I'm
the result you mentioned that they extend to multi-sample.
Yes, exactly. I didn't say it. Sorry. Okay, good. So just to summarize this multi-pack thing, first of all, I think it's a very kind of general and appealing notion that really enhances the guarantees of what people like machine learning people do on a daily basis, which is this regular loss minimization. The reduction to OI in some sense gives like this universal learning algorithm, right? Like whatever loss you want to use, there's a single algorithm. The only thing that differs is the construction of the distinguishers, which also have some dependence on the specific loss function that you care about by definition. And in a way, we've also established connections between kind of OI as a learning paradigm and agnostic pack, which is an established learning paradigm. And this is also very related to questions recently studied in this Omni predictors paper from ITCS. Okay, so with this, I can summarize, and I think I'm exactly on the 1 hour mark, which is nice. Okay, so I've discussed this notion of outcome indistinguishability, which is a new learning paradigm inspired by ideas from complexity and cryptography. And I've tried to demonstrate how it can be used to learn predictors that have kind of strong semantics in terms of how well they do on subgroups in the data. So I think that's it.
Well, thank you.
Thanks.
It's harder to give everybody chance to applaud, but everybody applauds, and now everybody can ask questions. But I have one basic question. You said nothing about this universal algorithm. How does it work, the OI algorithm?
Right. So I have a hidden slide, but I think it's technical. We don't need it. Basically, it's a very simple kind of a boosting style algorithm, where as long as there is a distinguisher that currently has success probability larger than epsilon, then I'm making this local update to my predictor to kind of make this distinguisher worse off. And then tying it all together is like a potential argument that says that I can't keep making these updates forever. At some point, I'm going to terminate. So
you need access to the family of A of potential distinguishers that allows you to update the distribution this way.
Exactly, and that's partly where the exponential dependence on the accuracy parameter comes in the Oracle access OI, because like this kind of ceases to be efficient access to the distinguishers. But I'm always thinking of the distinguishers as being like these small efficient testers. Mm-hmm. Yeah, and there are also some previous results on I've described as like enumerating over the distinguishers. You can replace this with like a learning, like an oracle that gives you the distinguisher, and then you can show that this is like as hard as learning this class of distinguishers computationally.
More questions? What happened? Oh, you ran out of questions.
Yeah, I can ask more if you want. I can also ask the same question several times.
You can test for the consistency of our responses.
Yeah. No, I mean, but actually, I do care about understanding this thing about the sizes of the subgroups. I mean, it could have made sense to somehow ignore or there's something similar to what the guy said, maybe to somehow factor the size of the mass in the subgroup to how much we care about it.
Yeah, so there are a lot of, for example, when people define like approximate calibration, there are notions that kind of have this relative error where the error is allowed to scale with the size of the group inversely. We were not taking that route. I think of it as more of, it's like a choice. I don't think, these results would not go through in that setup.
Just because I imagine that in real life scenarios, you mentioned the Klalit thing, for example, you have some set of data and maybe you can't get more. And if you would restrict yourself too much, you wouldn't find many, I don't know.
So in practice, there are other ways to get around this, right? Like if you remember when I said that there are 360 subgroups, these are after filtering out the subgroups that are small and I don't want to, I don't want them to ruin my guarantees.
I see.
Yeah, it's just practical choices.
Yeah.
More questions? All right, Gal, thanks a lot.
Sure.